Such a simple story. Welcome to the weird and wonderful world of time travel. But of course, traveling freely through time is impossible, you might say. You can't simply visit yesterday or rush headlong through millennia. And yet, this too begin to emerge. First of all, who wrote the letter? The older version of you simply takes the letter they'd already been given as a teenager back in time. The letter is a seemingly creatorless entity stuck in a time loop. This is the Bootstrap Paradox. Repeating, you save your teenage self, so they grow up to travel back in time to save their teenage self, who grows up to travel back in time, and so on. You are stuck in a relentless cycle. It's not quite so straightforward. Despite its myriad impracticalities, there are slivers of possibility lurking at the edge of physics, temporal loopholes lying just out of reach. And so, the question arises, if time travel were to be possible, just how could we do it? In 2021, a researcher at Portsmouth University calculated that there are about 6 times 10 to the power of 80 bits of information in the observable universe. That's a 6 followed by 80 zeros. Information is incredibly valuable, and data brokers are collecting your eternalism is known as the block universe theory and is based on Albert Einstein's much-lauded general relativity, one of the most successful theories in the history of science. In 1905, Einstein publishes the special theory of relativity. It does away with Isaac Newton's notion of absolute time. There is no universal clock that everyone can use to agree on when something happens. Instead, as the name suggests, time is relative. Depending on how they move through space, one observer could see event A happen before event B, while another sees event B occur before event A. Both observers are equally correct. An event in your past could be in someone else's future. This is yet another reason why all our yesterdays cannot simply vanish. How can they, when the events they contain might form part of somebody else's tomorrows? As well as this, special relativity cemented the fact that space and time are not completely distinct from one another. In 1908, Hermann Minkowski develops Einstein's work and properly unites space and time once and for all. He says that moving through space affects how you measure time, because the 3 dimensions of space and one of time are actually woven together into a single fabric that he called space-time. But how do we know that space and time are actually bundled up together into the space-time that the block universe is made of? Proof would eventually come in tests of Einstein's general theory of relativity, which he presented to the world in 1915. Back in the 1840s, astronomers had harnessed Newtonian gravity to discover an entirely new planet. Using Newton's equations to predict the future path of Uranus, they had found that it appeared to deviate from that path. The French astronomer Urbain Le Verrier pored over the equations for months, searching for an answer. Was Newtonian gravity wrong after all? Not quite. Le Verrier suggested that an unseen, more distant planet pulls on Uranus and affects its orbit. If correct, Newton's laws of gravity would be vindicated, and in 1846, Neptune was found. Despite this success, and although he didn't know it yet, Le Verrier was about to hammer the first nail into Newtonian gravity's coffin. Planets don't have circular orbits, but slightly changing elliptical ones, with the sun offset from the center. Newtonian physics claimed that these slightly changing orbits was due to the gravitational pull of the other planets. And Newton's equations were correct in their predictions for all of them, except one, Mercury. Le Verrier realized this in 1859, and the search began for another new planet, but no such world was ever found. Instead, the answer came from Einstein. On the 18th of November 1915, he wrote a letter to the German mathematician David Hilbert. Today I am presenting a paper in which I derive out of general relativity the perihelion motion of Mercury, discovered by Le Verrier. No gravitation theory had achieved this until now. Imagine the fabric of space-time as the surface of a trampoline. If you place something heavy in the center, it will sag in the middle. Likewise, the presence of a massive object like the sun creates a dip in the fabric of space-time. Physicists call this a gravity well. Einstein was arguing that there is no Newtonian gravitational pull at all. It is merely a mirage. As the innermost planet, Mercury moves more deeply into the Sun's gravity well than its neighbours. The deeper it goes, the more the local space-time becomes curved, and it's this increased curvature that causes Mercury's orbit to change. For all the other planets, the curvature is subtle enough that Newtonian gravity gives the same answer. Only in the extreme gravitational environment that Mercury inhabits does Newtonian gravity show itself for what it really is, a good approximation. Gravity is not a pull. It's the result of curved space-time. Since then, astronomers have tested this idea in myriad ways, from solar eclipses to swirling black holes and rippling gravitational waves. And in every experiment, space-time passes with flying colors. Our entire cosmos of past, present, and future, merely a four-dimensional block of malleable space-time that just sits there. A supernatural being that could somehow look upon it from the outside world would clearly see yesterday, today, and tomorrow, happily coexisting. But where did this all come from? As with everything else, scientists believe that the Big Bang birthed all of space-time. In other words, all of space and all of time. The regions of time we refer to as the past, the present, and the future are all there together in their entirety. And so it's as easy for two people to exist then and now as they do here and there. They can be separated by centuries of a physically stationary object moves because its time coordinate is constantly changing as second ticks after second, and today relentlessly becomes tomorrow. Join all the dots belonging to one particle, and you have a line that maps out its path through the block universe. A world line. You are nothing but a collection of particle world lines woven together, a knot in space-time, shedding and absorbing new world lines as you move towards the day the knot that is you undoes itself, or is undone. All the actions you will ever take, from what you'll have for breakfast every day, to if and who you'll marry, and the houses and jobs you'll flip between, are all entirely mapped out. You can't. It seems that the door to time travel is well and truly open. In a distant corner of the universe, a gargantuan supermassive black hole is holding sway over an entire galaxy. Its intense gravity is pulling, stretching, and ripping up whole solar systems. Hot gas and dust whirl around it as its huge magnetic field spins up and spits out shrapnel into the void. Among this debris is a tiny subatomic bullet, a proton, which races across the cosmos as close to the speed of light as it's practically possible to get. It has 100 quintillion times more energy than an ordinary particle of light, and after traveling over 1 billion light-years, it slams into Earth's atmosphere with 21 million times the energy of collisions inside the famed Large Hadron Collider at CERN. It is so energetic that to this day, astronomers know it as the "Oh my God" particle. An example of an ultra-high energy cosmic ray, it is a reminder that the Earth sits in a celestial shooting gallery, and when rays like this one strike our atmosphere, the impact is so violent that it bursts into an invisible fireworks display of subatomic particles. Pions, muons, and neutrinos erupt and cascade down to the ground. In fact, cosmic rays are so plentiful that they give you an annual dose of radiation equivalent to 3 chest X-rays. And for one Italian physicist, cosmic rays became an obsession. His groundbreaking work on the muons created by cosmic rays, producing some of the first evidence that time travel to the future is not only possible, but commonplace. And his name was Bruno Rossi. Rossi is behind the wheel of an old bus, snaking along the highest road in the world where pine trees compete with snow-capped mountains to reach the sky. Eventually, he arrives at the place he's driven over 1,000 miles from Chicago to reach, Echo Lake. Nestled high up in the Mount Evans wilderness of Colorado, part of the world-famous Rocky Mountains, it sits almost 2,300 meters above sea level. Up in the mountains, Rossi is measuring the muons created by cosmic rays. Muons are unstable particles, and so they quickly break down or decay. Physicists call the time it takes for half of a group of muons to make this change their half-life. It is just 1.56 millionths of a second. But Rossi's measurements reveal something curious. far more muons. Einstein's special theory of relativity says that you can think of anything moving through space-time as having a budget equal to the speed of light. The more of that budget you spend on moving fast through space, the less you spend on time. As the muons are traveling at close to the speed of light, considerably less time passes for them than for Rossi. From their perspective, fewer half-lives have elapsed, and so there simply hasn't been enough time for 99.9% of them to decay. This effect is called relativistic time dilation, and when Rossi factored it in, exactly the right number of muons reach the ground. But you may ask, does this really count as time travel? Imagine instead that you are the muon, but instead of traveling from the upper atmosphere to Echo Lake, you travel on a big loop around the universe at the same 98% of the speed of light and return home 25 years older. Those of us left on Earth will have been spending less of our space-time budget on speed than you, and so it will cost us more in time. But to us, you have spent your budget differently, foregoing time to travel through space. 25 years may have passed for you while you were gone, but 125 have elapsed on Earth. You have skipped forward a whole century. Indeed, such a journey could mess with the normal generational order of family relationships, as is poignantly explored in the short story Memories of My Mother by Ken Liu. And so time travel to the future is more than possible. We just have to accelerate humans to close to light speed. That is far from straightforward, however, because the faster you travel, the more energy you have. Einstein's famous equation E=mc² tells us that energy and mass are interchangeable, so if you gain energy, you also gain mass. In other words, the faster you travel, the heavier you get to an outside observer. A person traveling at 99.99% of the speed of light would weigh almost 2 tons, or about the same as a rhino. And accelerating them to that speed would require as much energy as everyone on Earth currently uses in 3 months. Understandably, we are very far from pulling that off, but even today, time dilation leads to some bizarre consequences. Take Mark and Scott Kelly, both former NASA astronauts who also happen to be twins. Mark was born 6 minutes before his brother. However, Scott has spent about 10 times longer in space, 520 days to Mark's 54 days. During these extra days, Scott was whizzing through space-time faster than his brother, spending more of his budget on speed and less on time. In other words, more time has passed for Mark than for Scott. Mark may have started out life 6 minutes older than his twin, but he is now 6 minutes and 5 milliseconds older. Had Scott been traveling as fast as a muon instead, their age gap would have widened to nearly 6.5 years, despite initially being born on the same day. And as if that weren't enough, there is another entirely separate form of experimentally verified time dilation, a second way to time travel into the future. Picture a clock, except this clock works differently to any you've seen hanging on a wall. It is simply made of 2 horizontal mirrors. A beam of light bounces between the 2 mirrors, and every time the light hits a mirror, the clock ticks. Let's imagine you have 2 identical copies of this clock. You set them running before taking one of them deep inside a gravity well, like the ones explored in the last section. Space-time is more curved inside a gravity well, and so the space-time between the clock's mirrors will also be curved. The beam of light will have no option but to follow this longer, curved path. In other words, the clock will now tick less frequently than the clock you've left behind far from the gravity well. Bring them back together, and more time will have elapsed on the clock that did not encounter the gravity well. But how can this be used to time travel into the future? Well, go and enter a deep gravity well and then return to Earth. More time will have passed on Earth than for you. You could hop forward a century, just as you did by traveling at close to the speed of light. However, to achieve a genuinely significant amount of time travel using this method, you'll need a very deep gravity well indeed, one far bigger than the Sun's. A supermassive black hole should do the trick as long as you're careful not to get sucked in. And just such a scenario was used as a key plot point in the film Interstellar, suggested by the famous physicist Kip Thorne. But Earth also creates its own gravity well in space-time. When Rossi drove his bus up the winding road to Mount Evans, he was moving further out of this well. In other words, he moved from a region where space-time was more curved to a region where it was less curved. He aged at a fractionally faster rate up the mountain than he did down the mountain. This difference is so tiny that a human is never going to notice, but atomic clocks do. The best are such good timekeepers that they are accurate to within a 15 billionth of a second every year. If you sync up two atomic clocks on the same shelf of a laboratory and then place them on shelves of different heights, they will noticeably drift out of time. Indeed, in 2022, physicists measured this gravitational time dilation using ultra-precise atomic clocks placed just a millimeter apart. And finally, your likely to release shuttle lands for the last time. In September, physicists make a shock announcement, one that rocks the scientific establishment. They seem to have observed particles called neutrinos traveling faster than the speed of light. If true, it would shatter one of the holiest doctrines in physics and open the door to backwards time travel. The bold claim comes from the Opera experiment buried deep under Italy's Gran Sasso mountain, designed to detect neutrinos fired 730 kilometers through the Earth from CERN near Geneva in Switzerland. Making that journey at the speed of light would take a mere 2.4 milliseconds. Yet some of the neutrinos appear to be taking 16 nanoseconds less than that. In other words, they seem to have gotten there traveling faster than the speed of light. Einstein's special theory of relativity says that the speed of light is an impenetrable barrier. The faster you travel, the heavier you get. The heavier you get, the more energy it takes to increase your speed further. Eventually, there comes a point when it requires an infinite amount of energy to increase your speed, so you can't. And that cutoff point is the speed of light. While a massless particle of light can travel at light speed, anything with mass cannot reach light speed, let alone exceed it. And so, inevitably, within a year, the neutrino mystery was solved. The experimental equipment was faulty. The neutrinos weren't superluminal after all. The initial finding caused such a stir because traveling faster than light would allow you to travel backwards in time. And the story of why starts with a young Dutchman by the name of Willem Jacob van Stockholm. In 1937, van Stockholm publishes a paper with the seemingly dull title of The Gravitational Field of a Distribution of Particles Rotating About an Axis of Symmetry. While mundane in name, it was revolutionary in nature, for it showed that Einstein's equations allowed closed time-like curves in space-time. Our world lines usually stretch from the past to the future, but a closed time-like curve is a world line that doubles back on itself, closing a loop as it intersects the line at a previous point. A pensioner following such world lines could revisit the moment of their birth, or even save their teenage self from a car accident. Von Stockholm had demonstrated that, at least on paper, there is nothing in the general theory of relativity to forbid backwards time travel. Except that at first glance it seems bending your future world line into a closed time-like curve requires you to travel faster than the speed of light, to travel outside of what is known as your light cone. If your world line is the singular path that you actually take through the block universe, then your light cone represents all the paths that it would have been at least possible for you to take. Imagine that you are stationary in space, your world line moving forwards in a straight line through time only. What are your options for where you can go in the future? Well, assuming that we stick with special relativity, you are confined by the fact that nothing can travel faster than the speed of light, which is approximately 300,000 kilometers per second. 1 second from now, you cannot be more than 300,000 kilometers away from where you are currently. Yet you could be up to 600,000 kilometers away in 2 seconds, and 900,000 kilometers in 3. The further ahead in time you go, the bigger the region of space-time that your future world line is allowed to be in becomes. That's why it's called a light cone. The edges of the cone represent the furthest a beam of light can be from where it starts at any given point in space-time. And so unless you can travel faster than a beam of light, you are trapped within the same light cone. Meaning that in order to loop your future world line around so that it intersects with itself at an earlier point, you would have to leave your light cone. In other words, time travel to the past appears impossible unless you can move faster than the speed of light. But there is another way to do it. If you constantly tilt your light cone so that your closed time-like curve to yesterday is always within it. And to do this, you would need to encounter space-time with an incredibly high amount of curvature. In 1974, the American physicist Frank Tipler explored this very situation, specifically what would happen to a cylinder containing at least 10 times the mass of the Sun and rotating along its longest axis. He showed that following a precise spiraling trajectory around this cylinder would warp your local spacetime in such a way that your light cone would gradually tilt backwards. And as your world line must be somewhere within the cone, you would then be ferried from the present to the past. Visiting a tipless cylinder